was the NASLR president in 2021 and now acts as part of the Public Relations and Education Committee for NASLR. He has a bachelor's degree in geology and history from Allegheny College, Meadville, PA, and a master's degree in geochemistry from the University of Southern Mississippi. He was the recipient of the 2019 DEP's Secretary's Recognition Program Award for dedication. Our second speaker will be Brandon Deal. Brandon Deal is a 2001 graduate of Juniata College. In 2003, he started Earthwise Consulting, where he works with non-NGOs, local municipalities. Sorry, you guys know what I'm saying, right? And for-profit businesses, assisting them with project development, project management, and grant writing. He is a recipient of the Department of Army Commander's Award for Public Service. And in his spare time, he's a pro-board certified volunteer firefighter and ambulance driver. Todd Coleman is a Penn State University graduate in mining engineering, embarked on a remarkable career. He started at Bethlehem Mine Corp, gaining expertise in mining, and later joined Gwen Dobson and Foreman as a consultant engineer. In a significant move, he co-founded MineTech Engineers, Inc. in Altoona, PA, which he was renowned for its expertise in the active and abandoned mining industry, providing historical insights to environmental groups. Todd Coleman is a standout figure in mining and engineering. So up first, we have Mike Haney.
He's got most.
All right, folks, I'm trying to bring this up. Is that working?
Yeah.
Okay.
Close to PowerPoint.
Close this. And now what?
Go down to your start. Go down to the start menu. It's pulled up.
All right, bear with me, guys.
Right, left. There you go.
There we go.
All right.
Very good. Now, how do I run this thing?
View presentation.
View presentation. Sorry, guys.
And I think you can hit full screen. All right, that works too.
All right, we're up and we're running. Great. Thank you, Jamie, for the introduction.
Really got through it.
It's nice to see everybody. Good morning, ladies and gentlemen. Kevin, we're good. Good morning, ladies and gentlemen. It's really a pleasure to be here. I consider it an honor and a privilege to open up this conference, technical discussions, and I really mean it when I say it. It is good to see each one of you here. If you guys know me, you know how much it means to me when we can see each other and get together. If you don't know me yet, please find the time to come over and introduce yourself and start that networking thing. John was absolutely right. That's really what these things are about. The tech presentations are gravy, they're nice, but it really is an opportunity for us to network and get to know each other. And it's just such a privilege to be here. And on that note, before I jump in here, I would like to take the time to share something with you guys. It's a quote. It's a quote that means a lot to me and has meant a lot to me in my adult life and in my career. And it's poignant, and I think it has a lot of relevance for us today. So in his 1981 publication, With the Old Breed at Peleliu, Okinawa, former U.S. Marine, they're never former, but Eugene Sledge closed his narrative saying something like this: until the millennium arrives and the nations of this world cease trying to enslave one another, it will be necessary to accept one's responsibilities and make sacrifices for one's country. As the troops used to say, if the country is worth living in, it's worth fighting for. With privilege goes responsibility. And I brought that quote up this morning for this very reason. And I want to share this with you guys because I think we're all of the same mind and we're unified and pulling in the same direction as far as land reclamation goes. I believe firmly that if we are privileged to have the ability to do the right thing, then we do share a measure of responsibility to make sure that the right things get done. And as John said, very aptly, we join together as problem solvers. We really do. And it's really remarkable, and it's exciting to get into that line of work. So as we are privileged to work together with each other, let's accept the challenges and responsibilities that we face and keep getting really good things done here. It's just a privilege to work with you all. And again, let's take advantage of this networking opportunity. So the title of my presentation is Cooperative Mineland Reclamation Operations and Comprehensive Managed Watershed Planning. And there's really a couple key words there. One is cooperative and one is comprehensive. Okay, and I think I've touched on the cooperative nature so far. I'm gonna keep going through that. Comprehensive managed watershed planning is a large scale thing. And this morning, I just really want to get right off the bat by saying the objective of this presentation that I'm privileged to do alongside Todd and Brandon is to showcase some really good long-term, large-scale reclamation success on a watershed scale. This watershed that we're talking about today in Indiana County, PA, has both Title IV and V abandoned and active mining operations been conducted over a long time. But the efforts that have been made have been mutually beneficial. And there's been several different projects with different scope of works, different permitted actions, but they've all been cooperative and environmentally proactive. And it's just so key, because as we tackle these problems, we as humans want to take the path of least resistance, like water or electricity. And we would love for there to be an ideal administrative separation between Title IV and Title V, abandoned and active operations, so that we can just clearly identify how to take the means to solve these problems, take the right people, and get it done. And, you know, if it's abandoned mining, it's a certain set of folks. If it's active mining, it's a certain set of folks and a certain set of means. It's a very black and white picture that we pursue. But to put ourselves through a little reality check, we deal, and you all know very well, that we deal with multidimensional overlapping systems. When I say multidimensional, all I mean by that is multidimensional with 3D physical settings that move through that fourth dimension of time. So there's transient media, usually groundwater, and metals and pollutants that move through three-dimensional systems. And when I say overlapping, it's very literal. I mean, they lie atop each other, right? Strata, coal seams, coal mines, they're just overlapping. But through time, different things happen, okay? And the Crooked Creek watershed in Indiana County, PA is no different at all. It's got extensive historical coal mining features. There's ongoing reclamation activities that have been going on for quite some time we'll talk about. And there's still Title V active coal mine extraction going on in the watershed to date. So it's not black and white, folks. And when I say the word systems, overlapping systems, I'm a trained scientist. I think like this. That's just my default setting. When I use the word systems, I want to get us all on the same page. Systems in my lingo can be either closed or open. Closed systems are something that we've all been through in class and laboratory, where we control the conditions. We control the physical boundaries of our experiments. We control the temperature. We control the energy and the matter going into the system. And then we make measurements based on what we observe, right? And we identify properties and thermodynamics and things that just happen, and we use those, but then we apply them to the real world, and they're open systems, guys, right? Where energy and matter can be exchanged with the physical surroundings through time. So physical input almost constantly changes, right? And then the physical boundaries of these systems change. Sometimes we add a property. Sometimes we add some airspace because something's been piled up. Sometimes we can subtract the volume that used to occupy an airspace and all the constituents thereof. So we're dealing with open systems here, and there's programmatic challenges of dealing with open systems, and it's a question of provenance and influence. And when I say that, I mean it matters where something happened and when it happened. And it matters to us as a group of professionals here this morning because it has everything to do with the funding eligibility and the funding streams where which we gain the means to deal with these problems. It matters when we identify the responsible entities, whether that's a financial liability or the professional entities that are going to take the fund stream and turn it into meaningful projects. It also helps us define our scope of work, and we just have to consider the influence of what we do, because groundwater and surface water just doesn't hold still, right? It falls out of the sky, it piles up, gathers itself in, does what gravity does, and it moves through. So when it affects the periphery, it has everything to do with how we consider challenges, and it's really important that we tackle these problems with a cooperative nature. It's really crux to these things. So The mindset that our group at the BAMR has taken with a lot of the NGOs and partnering agencies is to design for versatility and partner with talent. A phrase that I'll borrow from when I grew up is cast a wide net and get good help. And I think that that's largely represented in the room today and who's viewing this online. To characterize the open system dynamics that I've been talking about, just characterize it. A snapshot in time is one thing, but to characterize how the systems work and what's influencing through time and make those kind of interpretations and communicate clearly is really important. We've identified effective partners in this room already this morning. We'll continue to do that and then just cooperate to creatively achieve goals. We'd like to operate on precedent and things that have been done in the past, models that have worked before, but sometimes we really need to think outside the box or even wonder, is there a box, or should we just think creatively? The system that I'm going to showcase this morning with these guys is represented in this aerial image. This is about 10 square miles. I don't know how well you guys can see that. I don't know if the lighting is doing you any favors. It looks like an aerial image, okay? we'll get a little bit more detail here, but this is the Crooked Creek Watershed in Indiana County. Some things that you'll note, my laser pointer works, this large area here, I'm going to talk about that quite a bit. I've got a couple stars. There's one right there, there's one down here, and then the circled area there. These stars are point source pollutional discharges, okay? The area that I first pointed to over here is a large tract of land where refuse has been deposited and removed. The red circle is an attempt in the past made to address this situation that we have learned from and are moving forward. That might be a little bit more clear to you guys this morning. It's just a topographic map. It's got the receiving stream in blue and the same points illustrated there. I'll get into a little bit more detail about what those points exactly are. But this watershed, as I keep mentioning time, I think it's important to pause this morning and recognize and appreciate the lives that have been spent, lived, loved, and worked in these areas. The Ernest, PA area and the Crooked Creek Watershed is really the beating heart of coal country. It has been. There's been extensive historical mining from the years of 1902 through 1965, primarily by the Rochester and Pittsburgh Coal Company that essentially built the town, brought lots of folks in. I mean, if you go to the Indiana University of Pennsylvania's archives and you Google this, you'll find stories and pictures and articles that will help you appreciate how these settings got there. You know, we can look at it with a cold scientific objective eye and say, okay, there's chemical constituents that we need to deal with here. But if we don't pause to appreciate the lives that were lived in this area, we're really missing something as a community. I've thrown some stats up there. If you guys are looking at these, you know, that picture there is the old company store. In 1925, I've learned that the miners' wages were $20 a week before the company store hit them for different charges or health benefits for their family. In the 1930s, there were maybe 1,200 miners and their families living in this area, working 7 days a week, multi-shift. In 1945, as World War II was ending up, there was over 1 million tons of coal extracted from the Ernest area. There was also a battery of 278 coke ovens. Okay, steel was the big motivation for the industrial development of this area. Sorry. So just pause and understand that there's a community built and thriving and went the rise and fall of this little watershed. And that's why we're dealing with these constituents that we're dealing with. I'm going to introduce you guys to some of the main suspects if we were building a dossier or a file about this watershed. The primary contaminant source area from the surface that we'd like to show you guys today is this Ernest refuse pile. It's that area I was pointing at. It was comprised of 94 acres of accumulated coal refuse from those mine complexes. Chemically speaking, it was high BTU and low sulfur, so it's valuable stuff. But the estimated volume of that pile was, give or take, 10 million cubic yards, okay? So think 94 acres at an average depth of about 100 feet. It was an unlined valley fill, okay, of stuff those guys didn't want to use because the stuff they were brought out was not much better. But it interrupted the drainage topography. The E&S, the stormwater was an uncontrolled setting. It just, everything we don't want it to be in the reclamation perspective. It was overlying an up dip of the easternmost deep mine workings, which we know as the Ernest 2 and 3 mine workings, to the south of the receiving stream known as McKee Run. So there's an aerial image. Todd's going to talk about this a little bit more, but there's an aerial image of that pile before it was reclaimed. It's just a really massive coal refuse pile. So 10 million cubic yards. And I placed it on that topographic map so you can appreciate the spatial location of that pile. Another primary contaminant source area in this watershed from the underground perspective, as I had mentioned, was the Ernest 2 and 3 mine pool. The mine pool area is comprised of over 2,400 acres of mine workings. Now, the entire complex that's connected to everything underground in this area is 21 square miles. So the hydrogeologically connected portion of that for the Crooked Creek watershed is only about 18% of that, comprised of over 2,400 acres. The drainage area for this particular area, though, is over 5,400 acres. The mine pool volume is just this massive number. It's 1.5 billion gallons of water, or storage capacity in those mine workings. The total mine pool area above the discharge elevations that you saw on the map comprised 508 acres, okay, but 314 million gallons of storage capacity in the elevations above the discharges. What that means is we have hydrostatic pressure pushing that much water out at those discharge elevations. So, there's 314 million gallons of storage capacity that's fluxing through. Okay, those mines were underlying, obviously, and directly down dip of the Ernest refuse pile with less than 100 feet of cover. In fact, much less than 100 feet. There's the topographic map with an overlay of the mine workings that are hydrogeologically connected that I spoke of. Pretty extensive. Okay, it's good to note here too this morning that strike and dip, the mine's kind of along strike. The dip is to the northwest. Now to those point source discharges. The Ernest Mine Portal was the easternmost of those stars on the map, and it was an Upper Freeport Mine Complex drift entry, and it's currently free flowing. Okay, the estimated surface elevation is about 1050. It's up dip and at higher elevation than the other discharge I'll talk about in a moment. That's about 1.4 miles from that other discharge. Okay, but it flows at about 630 gallons a minute presently. It used to be more than that. But we're talking about 330 plus million gallons per year, and it loads pollutants in the Crooked Creek watershed to the tune of 77,500 pounds per year of our normal mining constituents there, being the key run. Now, those last 2 points I'll kind of leave off. There's been a chemical shift in that loading rate, and there's been a flow shift at that point too, and I'll get into those details. It's kind of a teaser there, but there's a picture of the Ernest Mine Portal for you guys this morning. It's plain as day. What is that? It's a mine entry, and there's water pouring right out. There's a peek inside a little bit. You can really see far back into that. Okay. The other point source discharge to the west is known as the Fulton Shaft. Same mining complex. It's a shaft structure, largely collapsed. It doesn't look like a shaft. Now I'll show you a picture in a minute. It's about 10 feet topographically lower than that other discharge point at the Ernest Portal. Okay. It's also down dip. Its estimated flow right now is about 1,150 gallons a minute, okay, or maybe 604 million gallons a year. It loads pollutants into the stream as well to Fulton Run and Crooked Creek, okay, maybe 47,000 pounds per year. And it's also experienced some shifts in loading rate and flow, and I will get into that a little bit later. So if you want a teaser there, look real quick before too late. Okay, here's a picture of the Fulton Shaft. It's an upwelling in a swamp. Okay, you drive up to it and it just looks like a wetland. But if you see the bottom of the picture there, that water is really boiling. It's really difficult to measure the flow. We've made some interpretations regarding that. It was measured one time when the flow was less and there were easier apparatus installation opportunities there. But you see a lot of iron deposition, things like that. Fulton Shaft chemistry, I threw this in here just real quick. It's not terrible looking. Okay, it's average pH in the past year has been 6.7. The average iron concentration is only 8.2, so it's not that bad. That'll come into play in a little bit here. There's another picture of everything. So you have the refuse pile, you have the Ernest Mine Portal, really proximal to the refuse pile. You've got the Fulton Shaft down here, okay, down dip about 1.5 miles away. I'll talk about that red X in a moment, but the cumulative hydro impacts that we understand from these discharges at the moment are a combined total of 124,000 plus pounds per year of those mining metals, okay, when we combine those two masses there. The combined flow estimate from these things is about 1,800 gallons a minute, just shy of 1,800 gallons a minute, which translates to 928 million plus gallons per year coming out of that directly into the surface water. And it degrades significant receiving stream habitat for about 12.5 miles, and it has done so for some time. Now, that red X on the map, that's the previous attempt to address this watershed. In the 1970s, there was an Operation Scarlift treatment plant there. And I do not have the time this morning to go into too much detail, but suffice it to say that it ultimately failed in the relatively short term because of sludge disposal recirculation issues. Okay, and that has everything to do with the geologic structural control about where those materials are placed. Okay, so it was a great learning opportunity for us to understand, a lot more about sludge recirculation and where to get rid of this stuff and just move forward positively from that. Okay, it's there today. You can drive right past it. It's currently a brine water treatment for some oil and gas operations. Okay, with that, I'm going to hand things over to Todd Coleman from My Tech Engineers. He's been working with that coal refuse removal project that Robindale Energy Services has executed over a number of years, and he's going to tell you a little bit about it.
Yeah, thank you, Mike. With the construction of the multiple cogeneration plants around the Evansburg area, Cambria Cogen, Evansburg Power, the Culver plant that some of you toured with us yesterday, they were all built in the year of about 1988 to 1993. And with the construction of those plants began the scramble to acquire and permit long-term fuel supplies to feed those plants. Air Products Corporation from Allentown built the Cambria Cogen plant at the Mine 33 site, which again, we were toured there yesterday also. And in 1993, they entered into an agreement to buy the Lucerne and Ernest refuse piles from R&P. The Lucerne pile was located about 6 miles south of Indiana at the town of Homer City, and the Ernest pile was about 5 miles north of Indiana at the town of Ernest that Mike has showed you some of the history of. Each pile was projected at that time to contain 10 million tons of refuse, and the projections from Air Products at that time were they would consume 1 million tons per year at the plant. So they were looking at permitting a 20-year life for that plant. So my firm was retained by Air Products in 1994 to obtain the permitting, and they decided to permit both sites simultaneously. There were some differences in quality of the refuse at both sites, and the initial plans were they would have opportunity to blend off of both sites to the plant. The permitting involved getting a surface mine permit for refuse processing, return of alkaline ash to the sites, MPDES permits for discharge, and other ancillary permits regarding highway access and things like that. Both permits were ultimately issued in late 1995. The first fuel was taken from Ernest in 1997, and the last fuel from Ernest was removed in December of 2019. So do the math, it's 22 years. They were actually thinking 10 years at each site, but I'll get into that a little more later, how this project had some extended life out of it. And just for additional information, the last fuel from the Lucerne site will probably leave by the end of this year. Most industrial sites from the turn of the last century, probably up until environmental regulations came into play, maybe in the late 1960s, whether you were a mine, a mill, or some manufacturing facility, you typically dumped your waste product in your backyard. And the Ernest refuse site was no different. From this photo, you see the refuse pile. The town of Ernest is just northeast of this photo. You'll see the outline of the mine on there, and the mine entry, which we identified as our sample point, L7 discharge. The key run is the receiving stream running pretty much east to west, and access came off of Route 210 near the town of Ernest. It was a 95-acre deposition of refuse, and they basically blocked the valley in. And looking back at the old USGS folios, there was a stream channel up through that valley. At the nose of the pile, the refuse was about 130 foot in depth. And at the south end of the pile, at this end, the refuse was about 40 feet deep. The pile was basically flattened off on top into a plateau. So what that did was basically created a huge sponge, if you will. Looking at that photo from '93, there was absolutely no vegetation on the site. What you had was the top end of the unnamed trip to McKee Run coming down there and running into the back end of the pile, created a bit of an impoundment there, and that water was migrating through the pile. We had a secondary trib coming in off of this side. It was doing the same thing. And down here at the bottom end, there was another side trib that came down. At some point in the 70s, R&P had gone in there and actually installed 450 foot of 36-inch diameter reinforced concrete pipe. That pile was infringing on that trib, and rather than have it completely blocked off, they put the concrete pipe in to at least keep that flow moving to McKee Run. So what you had was, pile sucking up all of the precipitation events. Runoff was coming down, running into the pile and migrating. As Mike said, the geologic structure basically is from south to north, and the underlying topography also trended that way, south to north. The other point to know is that in 1974, subsidiary of R&P, Kent Coal Mining Company, obtained a surface mine permit, and there was actually a slurry impoundment contained on that refuse pile. They had a market at that point in time. They went in and harvested the silt out of there, dried it, and sold it. The initial thoughts were that Kent Coal probably extracted all that down to original ground. So when we did the initial field work for the site and meetings with DEP, everybody's assuming that pond's sitting on original ground, and so their comments were, well, even though it's a man-made impoundment, we're now considering it a wetland. So in your mining plan, you got to leave that wetland in place. You got to work around it. Well, we went out and did some drilling, and lo and behold, found out that they never got to the bottom, and there was still about 20 to 30 feet of refuse underneath that impoundment. If we had to let that impoundment in place, we were going to sacrifice about 700,000 tons of refuse that would have to be left there. That kind of defeated the whole point of trying to go in and do a complete cleanup. Why would we leave 700,000 tons of refuse in there just so we could save that wetland? So the ultimate meetings with DEP and the regulatory folks, they finally relented and agreed that we could remove that, and it will become part of our wetland mitigation plan post-reclamation. We had a couple other wetlands that were created by the water running into the pile. So at the end of the day, that impoundment area amounted to 7.4 acres. We had another 2.1, so there were 9.5 acres of wetlands, and a 1.5 to 1 mitigation factor. At the end of the day, we had to create 14.3 acres of mitigated wetlands. In the work that we did for the field work, we found 9 discharge points at the north end of the pile, all acidic, emanating from the pile or at the toe of the pile. And we installed weirs at all those points. And April 1994, we did bi-monthly sampling of flow and quality through October of 1995. In addition, we also put a weir in the bottom end of the unnamed trib, which was our point L52, and we're also monitoring the deep mine discharge, which was our point L7. So if we go to the next slide there, Scott, please.
That's you. It's down there. It's on the keyboard. Down there.
There we go. Okay. This is a composite of the Loading data, our hydrologic units 1 and 2 combined were the combined flows from the 9 discharge points emanating from the pile. When you look at loading numbers there, trouble seeing from here, 13, almost 14,000 pounds a day of acidity, 3,435 pounds of iron, 28 pounds per day of manganese, 960.3 pounds of aluminum. We also looked at the flow of the unnamed trib, and these units were in milligrams per liter. The average flow through that sampling period, 28.7 gallon a minute. Acidity was 2,810 milligrams per liter, iron 282, manganese 10.2 milligrams, aluminum 309.71. So clearly, the discharge is emanating from the pile. You were seeing the impact in the unnamed trib, and that water all eventually went into McKee Run. What you're seeing now is basically the finished product. What I will tell you is, from a common sense standpoint, if you're going to rebuild a stream channel, you would likely think, well, we'll start at the bottom and we'll work to the top, because that way we'll be building a dry channel. And, you know, when we get to the top end, then we'll cut the water in from the upstream trib. Well, unfortunately, that didn't work in this scenario. The economic and business model from the operator was and had to be that when a truck left with fuel for the plant, it's bringing back a load of ash. Basically, the return volume is about 90% with what they add in limestone, water for hydration. There was over 10 million tons of refuse taken from the site. We were permitted to bring back a little over 9 million yards of alkaline ash. So that being said, you couldn't start at the bottom end of the pile because the refuse is 130 feet deep. There's no way you could get enough refuse out of the way in the beginning to create enough area to immediately start placing ash. So consequently, you had to go to the south end of the pile where it was 40 feet thick, start trucking out, so you could immediately create airspace to begin ash placement. So that then brings the problem as you start to advance south to north. You now have the stream chasing you from behind. We had the benefit of this impoundment that had been created at the south end of the pile. At some point in time, they'd also put a gas line across there, so there was an earthen berm in place with a discharge pipe. But that impoundment was helpful to us in helping to control the upstream flow. In addition, there was water drawn out of there during the early parts, probably 100 to 200,000 gallons a day required for hydration of the ash as it was placed. So you managed the water as best you could. Obviously, the further down you went, the more exposure you had. As the mining advanced, they began reconstruction of the channel. We also brought in a secondary channel from off of this side, and ultimately reached the point where there was a sump established, and we installed 2 treatment ponds over at the east side of the site, and they would pump water from the sump to the treatment ponds for discharge to McKee Run. You monitored the weather because you made sure the sump was empty pre-big snowfall, pre-rainstorm, so that you could control that runoff for discharge. As I talked about, we were obligated to get into 14.3 acres of wetland mitigation. When we did the initial plan, maybe we were a bit naive in 1994. We had looked at creating basically one large wetland in the middle of that site. As we began the reclamation, and we did get to original ground over that whole 94-acre area. When you really took into account the slope of the original ground, and then think about trying to build a 14-acre wetland with basically a flat bottom on it. At the north end, you were going to end up with a rather massive ash fill to try to create that flat space. And the feeling was we were concerned about permeability and trying to maintain that water. So with much appreciation to the DP, district mining people, we're very cooperative as we basically modified the wetland mitigation plan on the fly as reclamation was being done. And what you see is a series of wetlands, A through E down through there, interconnected by the reconstructed channel. So what we did was stair step down the valley, if you will, coming into the first wetland, come down the channel, go into here, go to the next wetland, and kind of zigzag your way down through. The wetland C actually serves a secondary purpose. The stretch of channel coming down to C is rather steep. That C is our mitigation deep water wetland for the original impoundment we took out. So it almost serves as a surge basin. And then by going into the wetlands, we were able to slow the velocity as the water moves northward toward the key run. The wetlands, everything is in there and done now, site had been reseeded. When we continue to monitor the discharge points all through the life of the operation. And so we got to, as I said, last fuel came out in December of 19. Wetland work was done by 2021. It's hard for me to believe that by April of next year, I will have been involved with the site for 30 years. It's almost unheard of. I don't know how many of you can join that fraternity, if you will. I have been through 4 changes in ownership of the plant and that company, multiple plant operators, multiple foremen. We had multiple buyers came in with consultants, and we were kind of the constant through the whole thing because we had been involved from the beginning. So at 30 years, it's almost as though I had a slow motion view of what happened out here. We often get caught in society today looking for the quickest fix and a result. And I have to tell you that in this situation, perhaps slow and steady wins the race, and it's taken a long time to see the results. So what's the bottom line here? You see the numbers I showed you before, and now we look at the 2023 numbers for our combined discharge points. Out of those 9, 5 were eliminated completely coming off the pile. One of the other 4 very rarely flows pretty much in result of a direct precipitation event just because of its location. The other 3 flows have diminished incredibly. So you're now looking at acid loading of 26 pounds, iron loading 0.11 pounds, manganese loading 0.45, aluminum 4 pounds. You look at the bottom numbers there in yellow, we were well over 98, almost 100% reduction in the loadings of acid and metals into the key run. The interesting part is when you look at the flow, once we reestablish the total length of that channel from the south end to the north end was about 3,900 feet. Because of the way we positioned the wetlands in there, we didn't quite construct that much actual channel. But when you look at the downstream flow now in 2023, our data average flow is 151 gallon a minute. Our acidity, manganese, or milligrams per liter, 16.75, iron 1.7, manganese 1.4, aluminum 0.67. Again, we're looking at, in the 90s reduction for most of those concentrations, 86% reduction, 526% increase in the flow. Clearly, we flipped the narrative. All that water that was migrating through the pile, presenting itself as a downgradient discharge, we've now put back on the surface. Very gratifying to stand at the bottom end and stand down there at that channel and see, 150 gallon of alkaline water coming and, flowing into the key run. So it's really been, it's been a fun ride for 30 years. to see everything that happened out there. And again, appreciation to DEP for their cooperation. So many times they look for an exact design, exactly how you're going to mine it, exactly how you're going to reclaim it. In the mining world, that doesn't often happen. And in the reclamation world, they were most cooperative as we adapted to what we had in the field. And without a doubt, this has been a huge success story. Just real quickly on the other point, you know, when this was done, we figured 10 years of earnest, so 1997, you thought it should be done in earnest in 2007. CERN would be done in 2017. The extension of time really was due to the fact that because of the quality of earnest, allowed the operators to bring in refuse from many other additional piles. So this pile aided in the reclamation of other sites and other watersheds because they were able to bring that fuel in to the plant from other satellite piles. So that really was the point of, or the cause for the extension of time that it took. But that extension was well worth it. At the Lucerne site, we also did wetland mitigation over there. About half of that site is fully reclaimed and working on the rest. So it's just been a huge positive impact on the watershed, and the numbers are impressive. Thank you.
Okay, folks, time is an issue. I know slow and steady wins the race, and the race has been one, but I have about 2 minutes maybe to close this one up. We've got a whole agenda in front of us. So Brandon and I are going to take you through what I call the micro machines narration now. Do you remember those old commercials with the micro machine guy that had to talk to the past? That was really the game changer. That refuse removal was the game changer. What it did in our open system was it displaced the flow from one of those discharge locations to another. Really, the Ernest portal flow was reduced by 50%. That was displaced down to the Fulton shaft, okay? Just note that the flow is displaced. See, there's a graph. This was the old flow. That's the new flow, 50% reduction, okay? The other open system variable that changed was the mine pool composition is detected at the Ernest portal, okay? There's a lot of verbiage here. What you guys need to know is that the pH increased from the low 4s to about 7, okay? The metals decreased from a lot to not very much. This is the entire graph. That curve right there is the pH over time. These are the metals loading coming out of the Ernest portal. See how the metals just drop and pH goes up? That's interpreted to be the result of that refuse removal, okay? So if I can speak for Brandon real quickly, the figure here shows all of the features that you see here and also the plans for a Title IV treatment plant, okay, that's going to attack the Ernest mine pool and eliminate these discharges. And because of that chemical shift, there's a cost savings multiplier of 2.9. That water is going to be almost 3 times cheaper to treat if and when this plant, which is currently been applied for and is pending through the bill funding, will be installed. There's a conceptual view of the plant. Happy to talk to you about that situation. And I'll turn it over.
You keep going. Keep
Okay.
going. I want to
Brandon-
stand over here. The pictures are what's
Brandon was going to stand up here and he's provided me with these slides because those of you in the audience, and there are many of you that know the story of the St. Michael's plant, we're following a parallel course for the St. Michael's plant. There's an active mining entity, Rosebud Mining Company, has donated the design for the plant that's going to be constructed in the Ernest watershed. Okay, and very similar to the St. Michael's situation, we're gonna operate that at almost 3 times cheaper, than it would have otherwise been. So we have Title IV loading features, Title V permits taking refuse out from yesteryear. We have a Title V entity in Rosebud Mining Company designing a treatment system that's applied for to treat Title IV water. When I say cooperative, that's capital C cooperative, right? And when we say managed watershed, this isn't just a watershed we can walk away from. It's one that we're going to have to maintain a presence in. We're going to have to maintain and operate that treatment system over time. So we can't just call it a restored watershed. We're calling it a managed watershed. Okay, but this is a huge success story. Everybody that lives here has always said it's hopeless. It's too big. It's too expensive. You can't get it done. It's always been there, and it will always be there. And that's just not the case in the Cricker Creek watershed because of this cooperative operative nature. We're problem solvers, but we can't do it alone. We have to do it together. We got to do it creatively, and we have to wait for processes to happen over time. So we have cast a wide net, and we have gotten good help over time. Great things have happened in the Ernest area in Cricket Creek Watershed. So we have a grateful acknowledgement page to all the cooperating entities here. If you see your emblem there, thank you, thank you, thank you. If you don't, find me later and beat me up. Many thanks with that. And, it's just an honor to be here. I have a couple slides to explain some Q&A. We don't have time for that. If you have questions, find me later. I'm happy to explain any of the conceptual processes, the data, the results, the quantifiables that has anything to do with this. Thank you.
We have time for one really quick question. If anyone has a burning question that they want to ask. If not, then thank you all. Yes?
You were just gonna say, go to break?
Yeah.
Okay. I just want to add, we're going to go to break now, but all these presentations are being recorded and on NASLR's YouTube channel, you can look at later. I've got to do some editing, but probably next week, all these presentations will be live streamed. You can just download it and watch them as you go. All right. Cookies.